So I'm going to end the day by giving a tour in work CBA is doing in future of manufacturing, starting from today and ending about 50 years from now, with some surprising, certainly surprising to me, broader implications. So as background, CBA was created to study the digital physical boundary. We did things like the first quantum computing, cryptography, and materials. We were part of creating synthetic life in minimal organisms. That's the kind of research at that boundary. And then students from the program have done things like Jason built and runs Facebook's computers, Rafi built and ran Twitter's computers. To do that, because you can't believe in computer science, you have to believe in physics, essentially. So that's background on the program. And what's coming out of it is, this is time, this is Gordon Moore's original data, this is 50 years of Moore's law, and then this is my most recent book. This is 10 years of scaling one measure of digital fabrication around Fab Labs that's been scaling exponentially for a decade. It's more data than Gordon Moore had. And so I want to end the day by asking, one way to view what I want to do is ask what happens if this continues for 50 years of scaling digital fabrication. So MIT invented computerized machining in 1952. That's the first time a computer was connected to a milling machine. And the computer was digital, the machine was analog in ways that I'll talk about. The lab I run now, you can think of as successors to that. We have roughly, what we proposed originally to the NSF was one of every tool to make anything of any size. And that's roughly what ended up happening. So these are the tools we use to do that research. And along the way, we've done a lot of work on improving machine building. We spent off billions of dollars in companies to make rapid prototyping faster, cheaper, more accessible. So these are some of the companies we've spun off to do machine building. Formlabs, for example, a local one, is worth about $2 billion. Their latest investment round was about $200 million. So that's machines that are faster, better, cheaper, but you still have to buy them from them. So one step a little further out is not rapid prototyping, but rapid prototyping of rapid prototyping. This is work on open architectures for rapid prototyping of rapid prototyping machines, so you can make the machines as easily as the project. So there's parametric machine generators that let you design degrees of freedom. And then we needed to blow up the traditional control architectures in the machine to develop distributed data flow networks in hardware. And then we overlay distributed data flow networks in software. So the machine control is virtual. So if you want to go from open loop to closed loop or 3 or 4 or 5 degrees of freedom, you can add degrees of freedom to the machine, but there's no state in the machine that you have to trip over in doing that in the architecture. And that spun off an interesting project that overlaps in an interesting way with what Wojciech spoke about. We're working with the NIST Materials Genome Initiative, National Initiative on Advanced Materials, and the DOE's Manufacturing Science Program. They're based on expanding use of advanced materials, but there's a big feedback loop from developing a material to characterizing the material to developing a model of the material to introducing it in a process. So in this NIST project, we're developing bringing the rapid machine building to material science to develop open designs of machines that can measure materials, but in particular not measuring a particular single degree of freedom, but process the materials and then are instrumented to have enough data that you can develop predictive models of the material properties from watching them in use that you can then feed back into design workflows. And what's emerging from that with NIST is what we've called the idea of computational metrology, that instead of just a rheometer measuring rheology or a tensile tester measuring a modulus, you measure predictive models by having a rich enough processing to characterize the machine. So building that loop of sort of measuring models from materials, and very strongly driven by expanding use of recycled renewable materials that are very hard to model and have a lot of variability with this sort of these measurements. So all of that is near-term. Companies we've spun off for machine building, fairly short-term work with NIST or DOE. But that assumes the materials are analog. You continuously process them. And that sounds obvious, but isn't and shouldn't be. So if you go back to the 1952 NC mill, all of the data was in the computer, and there's no information in the material. So errors accumulate, there's no state in the material. I've been interested in coding the construction of the materials themselves, digitizing the construction of the materials. So all the lessons Shannon and von Neumann taught us applied. So if you think about a child playing with Lego bricks or amino acids, they have same core properties, which is global geometry comes from local constraints. You don't need a ruler or a gantry. You can detect and correct errors, so the final structure is more accurate than the thing that assembles it. You can join heterogeneous properties, and you can unbuild. And so thinking about discretizing the materials earlier on led to this project where we were working with Spirit Aero on how to join large composite structures, where gluing composites is a vulnerability. And rather than developing a better glue, we blew up the structure into linking lots of small loops of carbon fiber. And we showed, by doing that at the boundary between being under-constrained and over-constrained, this is modulus versus density. This was the world's highest modulus ultralight materials. We increased it by an order of magnitude in this tooling-free process that was scalable, completely reversible by adding carbon fiber building blocks. Early on, this was in MIT's wind tunnel, using that to make a morphing structure. We showed by adding just a few part types, this is flexural, this is auxetic, negative Poisson, this is chiral. By adding those, you can create all of those material properties in a mechanical metamaterial. Starting with one base material, we can tune across this wide range of material properties by composing these simple building blocks in a discrete assembly. And so this is NASA Langley's biggest wind tunnel. This was a morphing aerostructure. A longstanding aero goal was eliminating control surfaces and having pure lift and roll by deforming the structure. But prior versions build complex mechanisms into the aerostructure. Here, we're sort of turning the whole structure into a mechanism by building it out of these cellular morphing building blocks. And so this is ongoing work we're currently doing with Airbus. An offshoot from that was, this is a project with Toyota, initially not starting with production cars, but looking at, with their zero emission division, the extremes of high efficiency. So this is a super efficiency race car. In the past, they'd spend a year developing design and tooling to make these. This was made in about a month end to end with these structural building blocks. And there were a number of surprises. The first day of the race, it was raining, the driver didn't have great visibility, and the first thing he did was crash. Everybody screamed, went running after him. And one of the surprises we didn't expect is the whole car just deformed around the crash and came back to its original shape. And then during the race, the driver found the vibration was significantly reduced, which we don't understand, but in this completely tooling-free process. And so for both Airbus and Toyota, what's so interesting about this is it potentially eliminates a lot of their supply chain, that final assembly becomes the only assembly by building out of these cellular building blocks. Another project in this group we're doing is with the Army Research Lab, where there are rigid robots, like a big dog, that are expensive, inflexible, but work well. And then there's soft robots that are expressive but very limited in performance, basic, and access. And so this is using these mechanical metamaterials here to make a drone. This is a legged walking creature. This is a swimming creature, just by composing these mechanical metamaterials. And it's sort of a third way from rigid versus soft robots that we can tune these very anisotropic properties. And what's interesting is you can actually assemble them in the field and disassemble them in a completely reversible process. So that's robotics work with the Army Research Lab. In turn, to build them, the cellular construction leads to a very interesting architecture for the automation. So these are robots that walk on the structure they're building. They navigate relative to the structure, the metrology I was describing. They error correct by whether you didn't or didn't place a block together. And so a little robot can make a big structure. And then there's a very natural decomposition for how these robots collaborate. And so we've done path planning for designs for swarms of these robots to do collective construction. And one of the most interesting things they can then make is themselves. So this was a first version of designing an assembler to build assemblers. And so this is an assembler building a small set of building blocks to make micro robots to then build the robotic assemblers I showed you. And so in a few steps, what that'll show is a rigid beam is rigid, a flexible beam bends, 2 flexible beams is parallel transport, 4 of those is a 4-bar linkage, a 1-bit actuator just clicks, but 2 of them is cyclical. And so this is a discretely assembled motor made out of just 3 or so part types. And we're working on complete robots made out of these building blocks that in turn can make the robots out of the building blocks, so self-assembling the robots. And it turns out you need that for scaling the throughput. The inspiration for this is the ribosome that makes you, the molecular assembler, is very slow. It does about 1 amino acid a second, but you can make an elephant that way because ribosomes make ribosomes, and you have trillions of ribosomes in a cell. And so you end up not doing a parallel or high-speed process, you do a massively parallel serial process by this recursion of the manufacturing process. As part of the process's manufacturing can build the assemblers in the process. And so that's why a big focus on this is automating the assembly of the assemblers to then make these cellular structures. And then a really surprising spin-off from that project, and again, this talk is a tour through a lot of projects in this space. I can tell you more details in the discussion, is to build these assembly robots, we needed to build in the intelligence. So we started packaging wafer-level chip-scale packages of the processors and working on very dense interconnect so that the assembler can place the intelligence of these assemblers for an assembler to build an assembler. And that led to work on just building computers that way. So today you need a $10 billion chip fab to make chips, and then they go into boards and blades and systems with very clear distinction at each scale. There's a kind of this firewall between how you describe a computation and the geometry to actually implement it. And so what this led to is the possibility that you can assemble you can fabricate 3-dimensional computing structures where you align the structure of the computation with the problem you're running on it. So it's sort of CAM for computation to construct computational structures. And one of the reasons we're doing it is a project with Lincoln Labs to do a superconducting version aiming at a 10 to the 5 reduction in power consumption. We're working on using this to make secure systems because you assemble the computation within a secure boundary. We're looking at AI applications where the AI system can learn the construction of its own hardware to align the representations of hardware and software, given the insane resource requirements right now on AI. We're looking at this for field reconfigurability of computation at the end of very long supply chains, all as this offshoot of discrete assembly now building computation. And more recently, that spun off a number of businesses. With the former number 2 at Amazon, the device work has spun off a direct write process for MEMS fabrication, atomic machines. The large area folding for the kind of structures I showed you has spun off a company for making electromagnetic devices. And the discrete assembly has spun off discrete lattice industries. One of the things they're targeting, for example, is making wind turbine blades and towers on site rather than shipping in huge things at long distances. So then the complexity of structures like these break the simulation tools. And so we're part of a DARPA program that's reflecting broader pain in the difficulty in simulation. And it's aiming to revisit how multiphysics modeling works. And in there, what we're doing is molecular dynamics is fundamental, but you can't do more than picoseconds of macroscopic time or length scales. We consider partial differential equations fundamental, but they're really the IT of a few centuries ago, and you need solvers to execute them. Everything in between we consider numerical methods, and I've been interested in the extent to which you can abstract just the very basic properties of propagation and interaction as a fundamental computational representation. There's a slew of about 15 acronyms of DEM, SPH, MPM, that are all names in niches of the idea of simulating with particles. And so what we've been developing is very efficient ways to take really simple models of just interacting particles, but design force laws to span multiphysics. So one of the places we're doing that is in carbon fiber failure, which is a notoriously difficult thing to model. So this was a test article where it starts shearing and pulling apart and cracking, and there hadn't been a technique that could simultaneously model the microstructure and the macrostructure, but by just scaling the propagation and interaction of particles, we're doing it in this single consistent framework. And so we're bringing in a range of physics to these multi-physics solvers. And then, in turn, once we have that, and this picks up from Wojciech's talk, the systems I'm describing become so complex it breaks the design tools. And we work closely with SolidWorks and Autodesk on the CAD, and the design tools break. And so Jan is a very interesting former DARPA program manager who had geometry and optimization at Boeing and went to DARPA to revisit design. And as part of that, I've been inspired by what was science's breakthrough of the year in morphogenesis. Your genome doesn't store the fact that you have 5 fingers. It stores you have a developmental program that when you run it, you get 5 fingers. And the reason that's profound, one is just compression, because you need to describe trillions of cells with billions of bases. But the more important one is almost any search you do over the genome is fatal or inconsequential, but not interesting. It's hard to innovate. The heart of AI is finding representations for search, and that's what the genome does. That one of the oldest, most carefully curated parts of the genome are called Hox genes, the part of the gene that codes for these developmental programs. And so there isn't really traditionally, maybe outside of a lab like Wojciech's, a notion where you design something by not actually designing the thing, you design the description that becomes the thing, but that crucial abstraction is essential for how evolution works. Otherwise, it would be doomed. And so we've been studying search over algorithmic descriptions. And so one of the warm-ups we did that was surprisingly difficult for us was just reproducing a few hundred years of mechanism design. So this was, could we discover involute gears by just sitting on top of these particle simulations, and then doing evolutionary search with probabilistic representations using the sort of algorithms Wojciech was describing to rediscover gear design, and then coming up with designs that caught up with traditional designs and for particular model cases could beat the performance of them. And so if you take all of this work that I just gave you a table of contents of skimming, we credit von Neumann and Turing for inventing modern computing. Von Neumann actually never wrote about the von Neumann architecture. He wrote a pretty dreadful memo about programming the EDVAC. And Turing's machine was never meant to be a computer architecture. We've been living with those for far too long. But both of them ended their life studying how a computation communicates its own constructions. So von Neumann studied self-reproducing automata, how an automata can communicate how to build the automata. Turing ended his life studying exactly the morphogenesis problem, how genes give rise to form. In both of their cases, those were theoretical. We're now at a point where you can actually do them experimentally. The work I'm showing you is leading up to this notion of merging communication and computation with this fabrication in this much deeper sense of not just information in the design, but information in the materials, so that you have a system rich enough for a computation to communicate its own construction, merging all three together. And so MIT made the first real-time computer in 1952, the Whirlwind. It spun off PDPs that made the internet. That inspired the Altair that created PCs, and then smartphones, and then Internet of Things. That went from 1 to 1,000 to 1,000,000 to 1,000,000,000 to 1,000,000,000,000. And very literally, so the Nest thermostat roughly has the capabilities of the PDP. So in the same sense, MIT made the NC Mill in 1952. I talk through machines to make, to rapid prototyping to assemblers, to self-assemblers. All of these are happening at the same time today. Versions of all of these are in the lab, but that ranges from today to 50 years out. And the historical lesson is we're right about here, right about just at the moment that's analogous to when the internet was developed. And at the transition, this is Kernighan and Ritchie at Bell Labs inventing Unix. What they're doing in that picture is in your pocket right now. And so we're right at that boundary. And so that in part inspired me, and in part I came to appreciate that from, I teach one of the most oversubscribed classes at MIT called How to Make Almost Anything. That was aimed at a few research students using the tools I showed you. Every year, hundreds of students try to get in. We've expanded to multiple labs at MIT and one at Harvard. And they do the most amazing things in it. Kelly made a device to save up screams. This is a web browser for parrots. This defends your personal space. This incredible personal expression in fabrication. And so that in turn inspired, for the National Science Foundation for outreach, we started setting up community labs, mini versions of the lab I described, that are sort of like the cost and complexity of the PDP. It fills a room, it's about 10 different machines, but together you can make almost anything with them. And they accidentally went viral. There's about 2,000 now in 150 countries, this network of these community labs. So to teach the skills in that, I teach a global version of the MIT classes, but now to students in labs all across the world. We're working with a number of companies on deploying these as part of their civic investments. It spawned a network of cities, including Bostonville, Somerville, and Cambridge, all signing up to this idea of not just being a smart city, but a fab city, having these tools as part of their infrastructure so cities can produce what they consume. In the Obama administration, we ran one at the White House. It's led to really interesting legislation just resubmitted.
I'm United States Congressman Bill Foster, and I'm one of the few members of the United States House of Representatives who was a scientist before entering politics. So I often tell people that I represent about 1/3 of the strategic reserve of physicists in Congress. But when I came into work each day in physics, my first stop often wasn't to my office computer or some meeting, but to the laboratory machine shop to check on the progress of some parts that I designed for an experiment or part of an accelerator. So I believe I can safely say that I'm the only member of the United States Congress that knows how to program numerically controlled machine tools. I'm proud to announce that I recently introduced legislation in the United States House of Representatives which supports the goals and mission of the National Fab Lab Network as in the best interest of our people and the best interest of promoting the goals of greater science and technical education, greater access to research and production tools, and empowerment of individuals to understand and use technology to improve their lives. You can think of the NFLN as a new kind of national lab in the United States that's a cloud laboratory, a national network of connected local labs. I've been lucky to have it.
So, and all of that was really brought home during the pandemic. Early on, we were approached about using all of these tools, what could we do? And that turned into a working group of a few hundred people who had never really worked together, of researchers, manufacturers, frontline medical workers, but also community activists and government regulatory people that did the research to develop a range of rapid prototyping solutions to help with the pandemic, and then deployed them globally, exactly filling in the space between one-off do-it-yourself and which can respond quickly but not scale, and mass manufacturing that can scale but not respond quickly. We produced things in the millions by coordinating distributed production, using this whole network as a distributed production infrastructure as sort of, as a peak of what that future could look like, where you go to market by shipping data and you do distributed local production. So that was a high-speed tour through a 50-year roadmap of manufacturing. I talk about all of those pieces in these articles and books, and if there's any time, I'll be happy to take questions. Thank you.
In the beginning, you talked about Moore's Law, and then what's going to happen.
Yeah, the Lasse's Law.
Can you give us your view of what's going to happen in terms of that curve going in the next 50 years? Does it flatten off?
You mean the Moore's Law curve?
Yeah, and all the other ones past that.
Yeah, so Moore's law, starting around 2015, started rolling off. There's emerging technology that can keep it a little bit further, but the point of that is what's been called Lass's law is like Moore's law, but for fabrication. And the best way to understand the difference is there seems to be an AI revolution, but if you look at ops per second in a state-of-the-art computer and an ops per second in a brain, they converged about a year or so ago. So they're converged. But if you look at the ops per second in your body constructing you, and you look at the ops per second in the chip fab making the chip, they're off by about 10 to the 8. And so the interesting question isn't squeaking a little bit more of Moore's law in digital fabrication. It's this exponential scaling. We're just at the beginning at scaling digital fabrication. You know, it didn't start in 1952 because that's analog manufacturing. Sort of digitizing the manufacturing process itself, we're just beginning to do that. And so, you know, my lab did the first significant quantum computations. That's looking at pushing this a little bit further out. But I think the really interesting question is to recognize that's run its course. This new scaling era is where you merge bits and atoms. It's not simply digital performance.
Thank you. Yeah. Neil, show my ignorance in this question, but you know, when you look at self-replicating biological systems, there are mutations
Yeah.
that occur, which is part of evolution. So I'm just wondering, when you talk about self-replicating digital systems, are there similar kinds of errors or mutations in the replication that occur, and how do you deal with those?
Yeah, so that's right at the heart of this project I described. And so evolution is much more interesting than it's casually described. Evolution casually described is random things happen and there's mutations. Again, most changes to the genome are either inconsequential or fatal. And so as a result, making a protein in a ribosome has an error rate of 10 to the minus 4. There's some checks that are done. So mixing chemicals has an error rate of maybe 10 to the minus 2. The ribosome is 10 to the minus 4 because you're docking amino acids. That's not good enough for the genome. DNA replication adds a layer of error correction, very carefully curated, that makes an error of 10 to the minus 8. That's what maintains the integrity of us. So evolution does not allow errors in most of the genome. There's sort of this carefully curated subset where innovation happens in evolution, this evo-devo boundary in what I call the Hox genes. And so evolution is innovating in very carefully curated places, and it's error correcting in almost everywhere else. There's a limit in how much error correction it does because there's a thermodynamic cost. And so the sort of junk places it doesn't matter, it doesn't worry about. The sensitive places, it carefully prevents errors. And there's like thermophile bacteria that add another layer of error correction, like 10 to the minus 12, so they never make mistakes. And then it creates a space where you can do the search in. And so in, for example, the DICE project I described, where we're developing sort of computers to make computers, it's very much the kind of work Wojciech was also describing, where you carefully represent the space in which you search, and you build a probabilistic model of that space, and then you allow innovation in that space. And so it's not simple random choice. You error correct where you need to do it, and you carefully allow places where you can do it. Now, also, one of the related things to that that's been surprising for us is once you set up these kind of evolutionary search systems, just how important the role of the person in the loop is. That consistently we find the evolutionary searches we teach in these spaces very quickly learn to cheat. They learn to do the letter but not the spirit. Like just that gear search I showed you, it discovered based on how we were rewarding performance that if it caught the gear and it went flying off, it would get some extra credit, so it designed gears that would catch. And so there was a crucial need for like the instructor to say, no, 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 that's not what I meant. And we keep finding that there's a really important role for the human in the loop.
Thank you very much.
Okay, thank you all.